So here we are going to prove this binomial theorem. So using this statement, usually they'll ask state and prove the binomial theorem. So state and prove binomial theorem. So then what is the statement of this binomial theorem? Statement C, for any positive integer n, a plus b whole to the power of n equals nc naught, first variable to the power of n, second variable to the power, you can write 0 or you can write n minus n, plus nc1, a power decreases, c n minus 1, b power increases. Next nc2, a to the power of n minus 2, b power 2. So like this, how many terms you want, you can write so on. Then the last term is ncn, a power n minus n, b power n. A power n minus n, or you can write a power 0, b to the power of n. Both are correct. So this is a statement of binomial theorem. So how to prove this one? Both left hand side and right hand side are equal. So how to prove this one means, so to do the proof we are using here mathematical induction method. So induction method. Let us prove this theorem. Let us prove this theorem by mathematical induction method. Mathematical induction. So then by using mathematical induction means, first consider principal value of n is nothing but the statement a plus b whole to the power of n, nc naught, a to the power of n, b power 0, nc1, a to the power of n minus 1, b power 0, nc2, a to the power of n minus 2, b power 2. As it is I am taking, so on. Then the last term is ncn. See, a power n minus n is nothing but 0, b to the power of n. So as it is I have taken as principal value of n according to the mathematical induction method. Now first we'll take the case 1. So what is case 1 here? Case 1. So case 1 says put n is equals to 1. So if I take n is equals to 1, left hand side. So what is there in the left hand side? A plus b whole to the power of n. A plus b whole to the power of n. So wherever n is there, I am going to substitute there by 1. Then this gives a plus b. Next, right hand side. So right hand side we have n terms. So we can't take all the terms, no. So take 2 terms. You can take complete right hand side also, you will get the same thing. So if I take 2 terms, nc naught. So what is the value of nc naught? So this is the combination term. So we have to do separately. We know the NCR formula, that is n factorial divided by n minus r factorial into r factorial. So if I substitute here nc naught, so that is n factorial by n minus 0 factorial into, see, r value is 0 factorial. So somewhere in combination chapter we know 0 factorial value is 1 and any variable or any constant to the power of 0, its value is 1. So based on that, a power 0 and b power 0. So both the values are 1. Now n factorial by n minus 0 is nothing but n factorial. 0 factorial value is 1. So if we simplify, finally we will get 1. Similarly, nc1, in the second term we have nc1. Even this value is also same. See, n factorial by n minus 1 factorial into 1 factorial. So this simplification, n minus 1 factorial, sorry, here we need to substitute, no. So what is the value of n is nothing but 1. So if I substitute n is equals to 1, 1 c naught, a power 1, b power 0, 1 c1, a power 0, b power 1. So now n is equals to 1 is nothing but 1 c1. 1 factorial by 1 minus 1, 0 factorial. Here 1 factorial is nothing but 1. So 1 factorial by 0 factorial means 1. 1 factorial means again it is 1. So 1 factorial cancel. Even this is also useful. So similarly here 1 c naught. Even this value is also 1. So finally this gives 1 c naught is 1, a power 1, b power 0 is 1, plus 1, a power 1, b. Then this gives totally a plus b. This gives totally a plus b. So this is separate. Now we'll take, so this is the case one. See, both left hand side value is a plus b and right hand side value is also a plus b. So therefore p of 1 is true. Next, case 2. So here first one we have taken directly n is equals to 1. But in case 2 we had to assume. So let us assume p of k is true for some k. See, in the statement for some positive integer n is there. No, instead of that n we have taken k is belongs to a natural number n. So we are assuming here n is equals to k. Then, so what does it mean means, so put n is equals to k. So if you put n is equals to k, then the statement, so p of k is equals a plus b whole to the power of k equals, see, in the complete statement wherever n is there, so everywhere we are going to put k. So k a c naught a to the power of k b power 0, kc1 a power k minus 1 b power 1, kc2 a to the power of k minus 2 b power 2, like this, so on. The last term whatever is there, that is kck a power 0 b power k. So the last term whatever is there, so just I have substituted that n in place of n, k. In place of n I have substituted by k. So then this is also proves. So next, therefore p of k is true. So this is case 2. Then the final step, that is case 3. So this is very, very important. So what is case 3 here? We have to prove n equals to k plus 1 is also true for some k belongs to n. For some k belongs to n and k plus 1 belongs to n. So now see, for some k plus 1 belongs to n. Okay, so according to the statement, what is there in the left hand side? So we have left hand side a plus b whole to the power of n. So this we are taken as a plus b whole to the power of k plus 1. In place of n we are substituted k plus 1. Then this expansion, so we can split now a plus b whole to the power of k into a plus b whole to the power of 1. See, bases are same. If we add the power, again we'll get back to a same step. A plus b whole to the power of k plus 1 are going to split into two bases. So bases are same, powers are different. So that we know in the expansions, so if the same base, so if we have the same base, then we can add, that is like this. So this we know according to the expansion, simple expansion, exponential formula this is. Now, so we already have a plus b whole to the power of k expansion in the right hand side. So that we have to substitute as it is, whatever is there here, no, same thing we can substitute it here as it is. Whatever is there in the case 2, as it is we can substitute it here. So because of space I am taking from here. So a plus b whole to the power of k, I am taking from the previous step. What is there in the right hand side? A plus b whole to the power of k is nothing but kc naught a to the power of k b power 0 plus, next we have kc1 a to the power of k minus 1 b power 1 plus kc2 a to the power of k minus 2 b2, so on kck a power 0 b power k. So I am repeating, a plus b whole to the power of k, whatever is there in the right hand side as it is I took here as it is. So this is only a plus b whole to the power of k. This is only a plus b whole to the power of k expansion. Remaining a plus b whole to the power of 1 we have to take as it is. A plus b whole to the power of 1. This I have carried as it is. I have not changed anything. This I took as it is. Now multiplication. See here, product of two terms are there. So that is why we have to do the multiplication. So how to multiply this? First, kc naught a to the power of k b power 0. Now start multiplication with the first variable. So what is the first variable here? A. So into this a. Next, plus kc1 a to the power of k minus 1 b power 1. So I am multiplying with the first variable, that is a. Similarly, kc2 a to the power of k minus 2 b2. So again I am multiplying with the first variable a, plus so on. So what is there here? Last term kck a power 0 b power k, and we are multiplying with the variable a. So this completes the first variable multiplication. So this completely multiplied with a. Next, plus again we have to do the multiplication with b. We have to do the multiplication with b. See, kc naught a power k b power 0 into this b. So that is why into this b, into b. Next, continuation plus second term kc1 a to the power of k minus 1 b power 1. So we are multiplying with the second variable b, right? So that b plus kc2 a to the power of k minus 2 b2, and we are multiplying with the second variable b plus so on kck a power 0 b power k and multiplied with the second variable b. So this completes the multiplication of a into complete term and b into complete term. Now we have to group the terms, then it is easy to expand. So to group the terms, first identify which terms we need to group it. So which are the terms we have to group it, first identify that. So now see here, first term there is no any common term here, so that is why we can take first term as it is kc naught. See, we already know any constant to the power of 0, that is nothing but 1. That means b power 0. So that means b power 0. So this value leads to 1. This value leads to 1. Only a power k, anyhow that is 1, right? Leave it. Into a. Into this a I took as it is. This plus kc1 see a to the power k minus 1, and here one a is there. So same logic I am applying. Bases are same, add the powers. Bases are same, add the powers. So how to add the powers here? See, I am going to do the rough work here. A to the power of k minus 1 into this a. So nothing else means understood power is 1. So this gives same logic I am applying. So bases are same, add the power. Same logic here also. Bases are same, add the power. So this totally gives k minus 1 plus 1. So minus 1 plus 1 cancels, then this gives only a power k. So that is this. Here also directly you can write, instead of this a, directly you can write k plus 1. How? So a to the power of k and a to the power of 1. That gives a to the power of k plus 1. Same logic. Bases are same, add the power. Into this b. Next, plus kc2 a to the power of k minus 2 b power 2 c. Here one a is there. So minus 2 and nothing else means power 1. So we can decrease, then that gives k minus 1. So plus 2, minus 2 plus 1, that gives minus 1. Like this. So on. The last term kck, any constant to the power of 0 is 1. 1 into b power k into a. So this is first one. Plus second term kc naught a to the power of k b power 0 is nothing but 1 under this b, plus continuation step is there here kc1 a to the power k minus 1. See, b power here 1 and understood nothing else means 1. b into b, b square. plus continuation. Next step, so b into b square I wrote. Next step, kc2 here, a to the power of k minus 2, b square into b cube, so on. The last term, kck, a to the power of 0 is 1, b to the power of k and b power nothing else means 1. So this gives b to the power of k plus 1. So this is the next simplification step. Next, so the continuation of this one, kc naught a to the power of k plus 1. So here we had to do the groupings, means we had to take the common terms. So which are the common terms that we need to identify first? See, in the first product and second product. So where we have to identify common terms means first product. See, here to here one bracket and next here to here it is another bracket. So this is completely multiplication of a coefficient, and next this second one is multiplication of b term. So that is why we have two terms. Now which are the common terms means, see, a to the power of kb, one common term. In the second product also we have the same like this, a to the power of k into b. So two common terms are there, so that we need to identify. Similarly, see, in the same another term is there, same way. So a to the power of k minus 1 b square, here also a to the power of k minus 1 b square. So if one more term is there, again we will get another term the same way. So like that we have to identify first common terms. For this there is no common term, so only single term, that is why I took as it is. This first one is single term, I took as it is. Next, plus. Now what is a common term here? A to the power of k into b, remaining kc1 plus, in the second case we have kc0. For these two, common term is a to the power of k into b. For these two, common term is a to the power of k into b. So that is why I wrote outside. Next, plus, same as it is, kc2. Next case I am taking plus, here kc1. For these two, what is a common term? A to the power of k minus 1 b square. See, again if I multiply this one, first one, I will get back to a same thing. So again second one. So even though if you multiply, you will get back to a previous step. Similarly, even if you multiply this, you will get back to a same step. So just I have taken here common terms. Nothing has changed here. Only I have extracted a common variables outside. Only I have extracted common terms outside. Next. So on. The last term, that is kck b to the power of k plus 1. Now, so after grouping the terms, next, see, first term take as it is, kc0 a to the power of k plus 1. See, we have grouped these two terms. So that is to make it single term, we have the formulas. So for this one we have grouped, for make it as single term we have the formulas. So which are those formulas to make a single term is k plus 1 c k plus 1. This value is also 1. How means ncn. This value is also 1. So based on that, even this value is also 1. This one formula. And another formula is there, nc0. So nc0 value is 1. How this one means we have already done here. How nc0 value is 1, we have already done here. Same way I wrote here. That means n plus 1 c0 Even this value is also 1. If you want, you can prove the same method. So you can prove by using this method, then you will get the same answer. So this is one formula and another is there. So this is one formula, the second formula and third formula. So third formula is very very important, which is that means KCR plus KC, see compared to this minus 1, compared to R, one value is less. So in such way, at the time you can add K plus 1 CR. So this is another formula. So this is very very important, because according to this formula only we are going to combine these two values. See, simple. So according to this formula, KCR value is 1 plus KC. See, compared to this one value is less. So that means lesser value compared to 1, the lesser value is 0. According to the formula, then this leads to K plus 1. What is R? R is nothing but 1. So then this has become K plus 1 C1. Then this common term is as it is. This common term is as it is. Plus, similarly the second one, KC2 plus KC1. This is also applied in this formula, K plus 1 C, which is our value here 2. So if you get confusion also, you can see the series 0, 1, the next value is 2. Undoubtedly you can continue. Then just observe the first variable, that is a power decreasing. A power decreasing. So here K plus 1, K minus 1, so like that. So next a to the power of K plus 1, the next value a to the power of K minus 1 B square. Here a to the power of K minus 1 B square. So on. As it is. Whatever is there, I wrote as it is. Etc. Then the last term. Last term. See. K plus 1. C K plus 1 is also 1. NCN is also 1. That means we can write now KCK. Just instead of N, K is there. So then KCK, K plus 1 CK. Both are same. So I can change it, right? K plus 1 CK plus 1. No difference for KCK and K plus 1 CK. Both the values are 1. If you want a proof, again go back to the same formula. Here, apply that, you will get the answer. Its coefficient b to the power K plus 1. That is the last term. Where is a here means a to the power of 0, that is already become 1. So that is why I am not writing this one. This one is not writing. Understood, a power 0 is 1. So that is why that term is not appearing here. This gives the completely, now if you observe, wherever n is there, K plus 1. See, just see here in the statement, wherever n is there, KC naught. So KC naught and K plus 1 C naught. So no difference. So you can write K plus 1. There is no difference. So now in place of n, K plus 1. Again a to the power of n plus 1. See, in place of n, K plus 1. Again in place of n, K plus 1. Here n minus 1. So plus 1 minus 1 cancelled, then only K is remaining. Here n value K plus 1 minus 2, then it is leads to minus 1 B square as it is. So on, the last one, K plus 1 C K plus 1, a power anyhow 0, b to the power of n is nothing but K plus 1. So we reached the final step. So which is P of k plus 1. So thus p of k plus 1 is also true. So hence by mathematical induction p of n is true for all n is belongs to n. So this is the binomial theorem.